Hello class. In this lesson we're going to learn about the connections between trigonometry and Pythagorean theorem. So once again, make sure you have SOHCAHTOA memorized. I'd like you to try this problem on your own, and I'll show you my solution. So they give us that the sine of theta is 1/2, and we want to know what is cosine of theta. So label your diagram and try to figure out what the answer is. Well, we know sine is opposite over hypotenuse. So we label our sides appropriately. We end up with 1 here and a 2 here. So we're looking for adjacent because cosine is adjacent over hypotenuse. So that's x. So one way to figure out what x is to use Pythagorean theorem. And we end up with square root of 3. Now maybe you notice that when the hypotenuse is double the length of one of the legs, you know it's a 30, 60, 90, so this would have to be square root of 3. Regardless of how you did it, that's the answer. And so cosine is square root of 3 over 2. I'd like you to try this example the same way. Make sure you write your answer in simplest radical form. So in this case, they give us sine again. So we're going to fill in the opposite and the hypotenuse. Opposite's 9. Opposite 7. Hypotenuse is 9. Adjacent is x. We don't know it. Now, this doesn't look like a special right triangle, so we got to use Pythagorean theorem. And we end up with 4 times the square root of 2. So that's our adjacent. So tangent is opposite over adjacent. And this is what we get, but we got to rationalize that denominator. So we multiply by square root of 2 over square root of 2, and we end up with 7 square root of 2 over 8. So how was Pythagorean theorem helpful here? What did we use it for? Well, we needed to find a missing leg. And once we knew that, we were able to find the value of the given trigonometric ratio. So here's an application to the Great Pyramid of Giza. And they're in this diagram, they're telling us that this angle measures about 53 degrees. And this segment right here along this face is called the slant height. It goes from the vertex to the midpoint of this base over here. And so what type of common right triangle do you think they used to model this triangle? Well, they give us that the sine of 53 is about 0.8. And how can we write 0.8 as a rational number in simplest form? A rational number has numerator and denominator that are both integers. And that would be 4/5. Now, we don't know the actual dimensions here, but we know that if we multiply 4 by some number and 5 by that same number, that's going to represent the lengths. So that's the same as 4x over 5x. And we know x isn't 0 here because they're lengths. And that's going to be opposite over hypotenuse. So if you fill in on a triangle, we have 4x, 5x, and what's the common Pythagorean triple? This would be 3x. So they probably used a 3, 4, 5 triangle. Now in reality, today, that angle is about 52 degrees. Why do you think that could happen? Well, over time, things can settle. So that angle might have gotten squished a little bit, and now it's closer to 52 degrees than 53. And why do you think they used 3, 4, 5? Well, those are all relatively small lengths, and it also gives us a nice triangle. There's no really, really small or really, really relatively large acute angle. So those are 2 possible reasons why they could have used that. So in this case, we're going to hold the hypotenuse of this triangle constant at 1. And we're going to use this to figure out another relationship between Pythagorean theorem and trigonometry. So in this case, when we talk about sine, we want the hypotenuse to be 1. So that means when we rewrite it as a fraction, we're going to write it as 0.8 over 1. And that's going to be opposite over hypotenuse. So see if we can figure out what the adjacent side is. Using Pythagorean theorem, or the fact that this is a 3, 4, 5, you should get 0.6. So using these facts, sine of theta is 0.8, cosine of theta is 0.6. How can we rewrite the lengths of the legs here? So instead of 0.8, what can we write here? Sine of theta. Instead of 0.6, we can say cosine of theta. So we're still talking about the right triangle from before. But what happens if we apply Pythagorean theorem to this particular triangle? What happens? We end up with sine of theta squared plus cosine of theta squared equals 1. And this is called the Pythagorean identity. It's very important in trigonometry. And this holds for any right triangle. So we're going to see that in general on the next slide. So we just saw it in the particular case where the sine of theta was 0.8. Well, let's take an arbitrarily chosen right triangle. So here we don't know any of the values for the side lengths or the angles aside from the 90-degree angle. So using Pythagorean theorem, what can we write? We can write that opposite squared plus adjacent squared is hypotenuse squared. And now we're going to divide both sides of this equation by hypotenuse squared, and you'll see why we're doing that in a moment. When we divide by hypotenuse squared, we know hypotenuse squared is non-zero because it's a length. We end up with sine squared plus cosine squared is 1. Now, why is that? Well, really, remember when you have a quotient, you can always use parentheses and put an exponent on the outside of that quotient, and that's equivalent. So this is really opposite over hypotenuse quantity squared. And the same holds here, and these are just 1. And a common way to write exponents for trigonometric functions is to put it in between the name of the function and the angle. So these two are really the same thing. This is still sine of theta squared, but it's just easier to write without parentheses, to put the exponent in between the name and the actual angle. So these are both the exact same equation, just written a little bit differently. And now we want to show why is tangent of theta equal to sine of theta over cosine of theta. Well, according to this diagram, sine is what? Sine would be A over C, cosine would be B over C, and tangent would be A over B. So see if you can fill in the blanks here and figure out why this equals tangent of theta. So we just do some basic arithmetic. Dividing is the same as multiplying by the reciprocal. The c's cancel, and that is tangent of theta. So now we're armed with two equations to help us with problems. We have the Pythagorean identity. Sine squared of theta plus cosine squared of theta is 1. And tangent of theta is sine theta over cosine theta. So now, without using a diagram, we can solve this problem by just using the Pythagorean identity. So let's see, what do we have there? We have sine of theta squared plus cosine of theta squared is 1. We know sine of theta is 1/2. And now it's just Pythagorean theorem, or just solving the formula. So that's 1/4. So cosine of theta squared is 3/4, right? Subtract that 1/4 from both sides. Take the square root of both sides. Square root of 3 doesn't simplify, and square root of 4 is 2. And one more example. So I want to figure out what is tangent of theta. So remember, in order to find tangent, we can do sine of theta divided by cosine of theta. So all we're missing here is cosine of theta. So let's see if we can solve this, and then I'll show you my solution. Using the Pythagorean identity, we substitute. We square this, subtract it from both sides, take the square root here, and we know square root of 32 is the same as 4 times square root of 2. Square root of 81 is 9. And now to find tangent, that's just sine divided by cosine. And we end up with 7 times the square root of 2 over 8. Right, we actually simplified this expression earlier in the lesson. So in this lesson, we learned about the Pythagorean identity, how to rewrite tangent, and how they can be useful in solving problems. Thank you for watching this video.